In the chapter Sound Wave, today we are going to start the discussion on the acoustics of building. Actually, this acoustics of building is a very important concept of sound wave, and it has a very practical application. In fact, when you talk about acoustics of building, there is a very important formula related to this, which is called Sabine's formula or Sabine's law. So basically, if you are talking about acoustics of building in physics, that means you have to discuss the Sabine's law or the Sabine's formula. Actually, what is this Sabine's law or Sabine's formula? We will learn, and we will also derive this. Now actually, if I would like to discuss the whole concept of this acoustics of building in only one lecture, the lecture will become lengthy, and that will be not joyful for you. So for your convenience, I would like to divide this lecture on acoustics of building in two parts. So today this is our first part of the lecture, or you can say this is part 1 of the lecture on acoustics of building. In fact, in this first part of the lecture on acoustics of building, we will simply define three terms or three concepts. First one is called reverberation. This is a phenomenon. What is this reverberation? Actually, I would like to explain this in this lecture. And after that, we will also learn about time of reverberation or period of reverberation. And finally, we will see what is Sabine's formula, which actually determines the time of reverberation. Okay? But in the next part of the lecture, we will actually discuss the growth and decay of sound energy in a live room, and in that manner we will be able to find the Sabine's formula. So deduction of Sabine's formula will be discussed in the next lecture, but what is this Sabine's formula we will see today. Okay? So now let us see first of all, in case of acoustics of building, a very important process takes place that is called reverberation. Okay? You can see, to understand the idea of reverberation, you can see this figure. Actually, this square which I have shown in this figure, this represents a closed hall, or you can say an enclosure. Okay? And let us consider that this S is a source of sound. This may be a speaker, this may be a person which speaks, okay, or any musical instrument that produces sound. So S in general is a source of sound wave, and this produces sound wave, okay, in this closed hall. Let us say this hall is denoted by H. So H is a closed hall, and S is a source of sound inside this hall, and it produces sound wave. Okay. Actually, the sound wave produced by this source is a continuous process. It continuously produces the sound. Okay. Now, the sound wave produced by this source, will incident on the different walls of the room, floor of the room, ceiling of the room. Okay. And if you consider that the wall, ceiling and roof of this room are reflecting, then definitely the sound wave will get reflected from the floor, from the wall and from the ceiling. And now an observer or a person, let us say here, you can see this is the observer or a person standing in this closed hall. Okay? Now you can see, I have shown here that a sound wave is emitted from the source, and it directly falls on the ear of this observer. without any reflection. So this first wave is the wave which falls on the observer's ear without suffering any reflection. But if you talk about this second wave, see here, this wave actually gets reflected from the floor and then it is received by the observer. But it is possible that a wave may suffer so many reflections before receiving by the observer from the different walls, floors and ceilings. For example, you can see this third number wave. You can see this is incident on this first wall, after that on this ceiling, and then on this third wall, and after that it is received by the observer. So after suffering a multiple reflection, the sound wave is received by this observer or this person. Okay. Now, actually a sound produced in a hall undergoes multiple reflection, as you can see, from the walls, floor and ceiling before it becomes inaudible. Now if you remove this source, once the source produces sound and the source is removed or stopped, now it does not produce sound. So after suffering so many reflections, a situation will come when the intensity of the sound wave becomes so smaller than that it becomes inaudible. You can't hear it. Okay. So a person in the hall continues to receive the successive reflections of progressively diminishing intensity, as you can see in this figure. And therefore, you can say the sound lasts for some time even after the source ceases to emit the sound. If the source is not emitting the sound, even after that, for some time interval, the observer receives the sound. Actually, this phenomenon of receiving sound when the source of sound has been stopped, that is called the process of reverberation or the phenomenon of reverberation. So you can define that reverberation is actually the phenomenon of the persistence of sound in a hall due to the multiple reflections even after the source stops emitting sound. Okay, such a phenomenon is called reverberation. Okay. In fact, this reverberation is a well-known familiar phenomenon in halls without furniture of a newly built building. Okay. So actually what I have explained regarding this reverberation, for your convenience I have written all those facts here. And so I will suggest you pause the video and note down these things in your notebook, because that will be a very good assignment or very good notes for your examination purpose. So I am just repeating that thing by giving the simple reading. You can see I have noted that sound produced in a closed hall, that is enclosure, continues to be heard for some time even after the source stops producing sound. And a sound produced in a hall undergoes multiple reflections from the walls, floor and ceiling before it becomes inaudible. Okay? And a person in the hall continues to receive successive reflections of progressively diminishing intensity, and therefore the sound lasts for some time even after the source ceases emitting sound. Even after that you will hear the sound. Actually, this persistence of sound in a hall due to multiple reflection even after the source stops emitting sound is known as reverberation. Okay. So what is reverberation? I think you have understand. If you remove the source, even after the removal of the source from the hall, you heard the sound due to the multiple reflection from the wall, ceiling and floor. And that phenomenon is called reverberation. Okay. Now actually this reverberation in a hall is not always useful. Okay. For example, if you are talking about an auditorium or a classroom, then if there is an excessive reverberation, that will be not actually desirable. Because in a classroom, if there is an excessive reverberation, the student who is hearing or listening his teacher, they will actually receive different notes at the same time. One directly from the teacher and another after reflection, and so they will get superposed and the fact will be not clear to the student. So in auditorium and classroom there should not be a larger reverberation, but there should be optimum reverberation, which is not very large or not very small. Okay. So in fact this reverberation is not necessary in case of a classroom or in case of a auditorium. But if you are talking about a concert hall where a music program takes place, then some reverberation is necessary. So you have actually when you have attended any concert in a hall, in a music room, then you have heard the echoes. That is actually due to the reverberation. Okay. So what is reverberation? I have explained and I think we have clearly understand. Now I would like to define a very important term which is called time of reverberation. And this time of reverberation is in general denoted by the symbol capital T. This is also called period of reverberation. Okay. So how this period of reverberation or time of reverberation is defined? Let us consider that there is a source of sound wave and initially the intensity of the sound wave produced by it, or you can say that the energy density of the wave produced by this source at the initial moment, let us say that is 10 to the power 6 times E. Why I have considered it as 10 to the power 6e, you will understand sometime later. And now consider, if this source produces sound and is stopped, then you know the intensity or the energy density of the sound wave in the room will get diminished, will get decreased. Okay? And there will be a time interval after which let us consider that its intensity becomes IF. This is final intensity. And that IF is equal to E. Okay? Equal to E. Or you can say that energy density falls from 10 to the power 6e to E. And what is this E? E is the minimum energy density that can be heard, that is audible. It means if the energy density, let us say E dashed, will become less than E, then the sound is not audible. So if the intensity of the sound wave decreases from 10 to the power 6e to E, where E is the threshold intensity, or you can say this is the reference intensity, which we have learned earlier that this is actually 10 to the power minus 12 watt per meter square. Okay. So if the initial value of intensity was 10 to the power 6 times of this threshold intensity, and after some time it becomes E, that is it becomes equal to the threshold intensity, then the time interval during which the intensity falls from 10 to the power 6e to e, that very time interval is called reverberation time or period of time. So I have mentioned here, you can see that it is the time required by the energy density or intensity to fall to the minimum audible value E, or minimum audible intensity, which is for human ear, that is 10 to the power minus 12 watt per meter square, from an initial STD value of 10 to the power 6e. What does it mean? It means it is the time interval during which million times of the intensity, initial intensity of the sound wave is decreased million times. It was initially 1 million E, and after some time it becomes simply E. The time during which the intensity or energy density falls to E from 10 to the power 6e, that time interval is called reverberation time. But where E is the minimum audible frequency, it means, intensity or density. It means if the energy density of sound in the hall will become less than E, your ear can't receive, your ear can't give response to it. Okay? It will be not audible. आप इसे नहीं सुन सकते. So you can say that reverberation time is the time interval during which the intensity of the sound wave becomes E, or you can say IF, from the value 10 to the power 6e to 10 to the power 6 IF. Okay. Now here IF is actually the final intensity or the final energy density, which is just audible. Okay. In fact, in my previous lecture I have discussed the intensity of sound, and you have seen that the intensity of sound is directly related to loudness of the sound, or you can say loudness is measured in terms of intensity. And you have also learnt that this loudness is measured on a logarithmic scale, which is called the decibel scale. So now, in terms of the loudness or decibel, you can also define this reverberation time. So let us see. If you consider that the initial value of intensity was 10 to the power 6e and its final value becomes E, then what will be the ratio of II and IF? This E and this E will cancel out. This is 10 to the power 6. Now you have seen that if when the intensity is II, then sound level is SL1, and when the intensity becomes IF, which is just audible, okay, then the sound level becomes SL2. So what is the decrease in sound level? Just you have learnt in my previous video that this decrease in sound level SLI minus SLF. So consider it SLI and SLF. You have learnt that this SLI minus SLF, that is decrease in sound level or diminish of sound level, how it is defined? This is 10 times log II divided by IF to the base 10. Actually, in that case, I have written I1 by I2. Here I have written II by IF. Okay. But as you know, if II by IF is equal to 10 to the power 6, then its decrease in sound level will be 60 dB. So, on the basis of this fact, you can also define the reverberation time in an alternative manner. So how now we can define the reverberation time? It is defined as the time interval in which the sound level is diminished by 60 dB after the source of sound is stopped emitting sound. When the source of sound is stopped and intensity is and the sound level decreases by 60 dB, the time taken in decreasing the sound level by 60 dB is called reverberation time. Okay. So I think now what is this reverberation time is very clear to you. Okay. In fact, this reverberation time for different type of room, the reverberation time has the optimum value which is differ from room to room. This depends on the shape and size of the room. For example, if you are talking about the optimum value of time of reverberation for a medium-sized room, then the optimum time of reverberation for a medium-sized room is 0.5 seconds. But if you are talking about an auditorium, then the optimum time of reverberation varies from 0.8 second to 1.5 second. This is the optimum value of time of reverberation in an auditorium. Okay. Now, for a music room, the optimum time of reverberation is from 1 second to 2 seconds. And for a temple, it is greater than 2 seconds. So these are some values of reverberation time, or you can say the optimum value of reverberation time for the different type of room. Okay. And so you should remember this data. Now, actually, what will be how this reverberation time actually varies, on what factors this reverberation time depends. From a series of experiments, a well-known scientist, Sabine, has found the factors which affect actually the time of reverberation. In fact, in his experiment, Sabine found that there are 3 factors affecting the time of reverberation. First one is the volume of the enclosure in which the sound is traveling, propagating. And another is the total absorption power of all the surfaces. That is nature of the surface, that is nature of the wall, ceiling and floor. Okay. And third one actually depends on the source which produces the sound wave, which I have not mentioned here. So if you consider that this T is the time of reverberation, then according to Sabine's law, this time of reverberation is directly proportional to the volume of the room, and it is inversely proportional to this capital A, where capital A is the total absorption power of all the surfaces of the room. Okay? And so you can say that this time of reverberation is proportional to V over A. Now when you will remove this proportionality sign, you must put here a constant. So T is equal to K times V over A. Here K is a constant. Okay. In fact, this A, which is the total absorption power, this is measured in Sabine. Sabine is the SI unit for measuring this total absorption power. In fact, what is this total absorption power? Let us now see. In fact, when sound wave is incident on a surface, basically 3 phenomena take place. A part of the energy will get reflected. This is in fact reflected energy. Another part of the energy will be transmitted in the another medium, and the remaining part of the energy gets absorbed by the surface. Okay. If you consider that there is no reflection and no transmission, then 100% energy will get absorbed, and such a surface is called perfect absorber. But in nature, there is no perfect absorber. Definitely, a part of energy will be reflected, another part will be transmitted, and the remaining part will get absorbed. On this basis, we define a number, a parameter, which is called absorption coefficient. And how this absorption coefficient is defined? It is defined as energy absorbed by a surface divided by energy incident on the surface. It means absorption coefficient is a ratio of the total energy absorbed by the surface and the total energy incident on the surface. If you consider that on a given surface, in a given time, EA is the amount of energy absorbed by the surface, and EI is the energy which incident on the surface. Then when you will divide this EA by EI, you will get a number, because in numerator and denominator both quantities are energy. And that very number is called absorption coefficient. Now you know this EA will be never greater than EI, because the absorbed energy will be never greater than incident energy. But in general, the absorbed energy is always less than incident energy, because some of the energy will also get reflected and transmitted. So definitely EA in general is less than EI. But if you consider ideally that our surface is a perfect absorber, it means there is no reflection of sound wave, no transmission of sound wave, only absorption takes place. In that condition, what energy is incident, all will get absorbed. So in that condition, you can say in case of a perfect absorbing surface, EA will be equal to EI. So in general, you can say that EA is less or equal to EI. And if EA is less or equal to EI, then this absorption coefficient A will be definitely less or equal to 1. Okay? And when it will be 1? It will be 1 only when the surface is a perfect absorber. Actually, an open window is an example of a perfect absorber. How? Let us think. If a window is open and a sound wave is incident on it, it will be reflected? Answer will be no. So it is not reflected, so we think that all the energy gets absorbed by the open window. And so an open window is treated like a perfect absorber, and for it we always take this absorption coefficient equal to 1. But if your floor of the room is made up of marble, for marble you can see the absorption coefficient is very small. This is 0.01. Okay. Now, if A is the absorption coefficient, okay, and you consider that the S is the area of a surface in a square feet, okay, then the total absorption power, this is equal to S, that is the total surface area, times A, where A is actually called the mean absorption coefficient. Why mean? Because you know, if there is a surface, the absorption coefficient at different position of this surface may be different. Because the physical condition of a different point on the same surface may be different. Okay? So if you consider that for a surface there are n values of absorption coefficients, These are A1, A2, A3 and so on, AN. In that condition, in calculation, we always define a mean value of absorption coefficient, and that will be defined as A1 plus A2 plus so on plus AN and divided by N. Or you can say this is summation over AI divided by N. This is called average or mean value of absorption coefficient. When you will multiply this average value of absorption coefficient by the area of the reflecting surface, then you will get the total absorption power A, capital A. So capital A, which represents the total absorption power, that is defined as S times A, where S is the total area which is measured in a square feet and A is the mean absorption coefficient. Okay. So this is this result which I have mentioned here, this is called Sabine's law. And as I have told you that in the next lecture, our aim is primarily to derive this Sabine's law. But for the derivation of Sabine's law, you must have to discuss the growth and decay of sound energy in a room, in a live room. So first of all, we will discuss in next lecture the growth of sound energy in a live room, and after that we will discuss the decay or decrease in sound energy in the live room. And you will see, after getting the result for decay of sound energy, we can obtain the Sabine's law. Okay. So this is this Sabine's derivation of Sabine's law is the subject matter of our forthcoming video. Okay. Thank you very much.